Yeah. But
All right, if you can turn to page 3. Okay, so we'll skip the warm-up problem. This is log differentiation. The idea is, yesterday we learned that there's all these properties available to us that can make our derivative process easier. And we're going to continue with that idea. Log differentiation is where we take a non-log function, so there's no logs to begin with, and we introduce logs into it so that we can take advantage of these properties and so that we can expand and so that we can have an easier time with our derivative. So here are the steps. First is we take the natural log of both sides. Anything we do to one side, as long as we balance with the other side, we haven't changed the overall value. Second, we simplify and expand using log properties. We have product property, quotient property, and power property available to us to take a condensed expression and split them up into easier portions to work with. Next up, we use implicit differentiation. The reason why we use implicit is because initially the y is by itself, but then once we introduce natural log to that side, then that y is going to be stuck inside natural log, and there's going to be a little bit of implicit, which means there's a little bit of dy dx that shows up. And finally, we just substitute. After we find the derivative, we just try to find a way to solve for dy dx. Okay. I think I'm going to bring this point and remind us that we only use log differentiation if there are no logs anywhere to be found in the problem. I see we make it to the point where we're always trying to do log differentiation, but if there's already a natural log in the problem, then if we add another layer of natural log, then you're overcomplicating. So if there's already a log or natural log in the equation, then we don't want to involve another layer of natural log or another log applied log differentiation. So here, example 1. Find the derivative of y equals x minus 2 squared over square root of x squared plus 1. Notice there are no logs here to begin with. The reason that we may want to introduce logs into the problem is because if we were to find the derivative, we could, but we'll have to go through quotient rule and chain rule, and possible, it's doable, but it's a lot. So with log differentiation, we're able to take this and split them up into easier and smaller chunks. So we'll take the natural log on both sides. And as we do this, we haven't done any, as we apply log differentiation or when we apply log properties, there's not going to be any calculus applied just yet. So we want to make sure that we don't just stop at the end of the expansion. We have to make sure that we keep in mind our derivative process is still needed at the end. Now that we have natural log introduced into both sides of the equation, now that right side can be expanded because we have quotient property, which says if I have natural log of A over B, I can expand that into natural log of A minus natural log of B, right? So we have this property to apply or to use. We can treat the numerator as our A value. We can treat the denominator as our B value. Now we're just trying to split this up using our properties here. Okay, we can continue with expansion in terms of power property, right? We can bring the exponent down. The radical is not an exponent, but we can make it into raise parentheses to the 1/2. Then we can bring this down. This is really just natural log of x squared plus 1 to the 1/2. Now that we have every term expanded nicely, we can apply our derivative rule. U prime over U for each of the terms. So notice now that y is not by itself, it's inside that natural log. So that is when we have to introduce implicit, when your y is kind of stuck inside something else. So the derivative for y is 1. So it's 1 over y, but because we're asking for y's derivative, we need to attach dy dx. So it's 1 over y times dy dx. All right, same process. If it was natural log of x, you would say 1 over x. But because it's natural log of y, we say 1 over y, but then we need that dy dx because of implicit. Okay? So this is our calculus step here. The 2 stays. Natural log of u becomes u prime over u, so 1 over x minus 2. The 1/2 stays, and then u prime over u. Now implicit, log differentiation is a little messy, so your derivative will just look like a whole sprawled out derivative, but that's okay. We don't have to ever clean up our answer with log differentiation. We can leave our derivative of one big mess, okay, and that's okay. So our process is easier, but our answer will look messier. So we have dy dx variable. Dy dx is kind of like our y prime. Our final step is to try to get this by itself. So dividing by 1 over y is same thing as what? Multiplying by y. So I'll say dy dx equals, bring the y over to the right side, and then we can just have all this as separate fractions. That's fine. I'm gonna do a little bit of cleanup here. I'll cancel off the 2's. You don't have to. So now we have our derivative. This represents the slope formula for whatever this graph looks like. And our final step is replacing the y back in terms of x. So because this started out as a function, we should be able to represent our derivative in just purely in terms of x. So I'm going to replace this whole expression in for that y. So your log differentiation answer will look a little messier. So this is one way that one instance when we would maybe make use of log differentiation when you have a really compacted expression and it's a bunch of terms that are being multiplied and divided, and there's exponents involved, and it looks like it would require a lot of multiple steps, quotient, chain, product rule, all combined together. And a compact expression with no logs in it would be a good candidate for log differentiation. The second example is one where we have to use log differentiation because this problem has no rules available to us. Okay. The reason why is because this is a variable expression raised to a variable exponent. And we don't have a rule that can handle a variable raised to a variable. We can handle a variable raised to a constant, right? This we can do using power rule. This is a polynomial here, right? But we can't handle a variable raised to a variable expression. So our workaround is we want to introduce logs into the problem. Great, thanks. And if we introduce logs into the problem, we can bring that exponent down, because right now this x raised to the x is an issue for us. So whenever you see a log raised to a variable raised to a variable, we can introduce logs into our equation to allow for that exponent to be placed elsewhere so that we have some rules available to us. So we'll take the natural log of both sides. Now, whenever you have a variable raised to a variable, you're always going to be expecting, well, I'll see if we can discover it. So now that we have natural log introduced into our equation, where can we now put this 2x plus 3? Yeah, coefficient. Now this is power property here, right? Normally, we can't just bring the exponent down, but because we're inside a log expression, we have that ability to do that. So once that 2x plus 3 comes down, it's now in front of natural log of x, but I want to find the derivative. Natural log of y is going to be the same as before, a little bit of implicit, 1 over y dy dx. But what's going to come of 2x plus 3 times natural log of x? What process do we have to go through to find the derivative here? What do you think? Product rule. You see that 2x plus 3 is its own thing multiplied by natural log of x. These are not inside each other. They're outside of each other. They're separated by a multiplication operation. So we have to go through product rule here. So whenever you see a variable raised to a variable and you use log differentiation, you should always be expecting product rule to show up. Okay. F prime g plus f g prime. All right. What's 2x plus 3's derivative? There's 2. G is natural log of x. Back to 2x plus 3. G prime. What's natural log of x? U prime over u, so what? 1 over x. Yeah. Just like before, we're going to move that y over to the right side, replace the y back in terms of x, and there's no need to clean up. As long as you can get your derivative on the right side in terms of just x, that's all we have to worry about. Right, I'll replace the y back in terms of x or back in terms of the original expression. Okay, we'll just skip the bottom curve sketching, and we're going to go to derivative of inverse at a point. Let's go to page 4. All right, let's just review a little bit with inverse functions. Inverse functions are functions where x's and y's are swapped. Domains and ranges are also swapped. So domain for one is range of the other. And graphs are going to end up being symmetric over the line y equals x. So the two graphs, if they're truly inverses of each other, we can fold the graph along the line y equals x, and the two graphs will overlap each other. Function must be one-to-one. They must pass a horizontal line test for it to be the inverse of a function. And a function is monotonic. That just means that it's always increasing or always decreasing. So that means like a graph like this will be considered monotonic. But something like this would not be monotonic because the graph is changing direction halfway through. But if a graph is always increasing or always decreasing, then it's considered it's just going in basically either going up, always increasing, right? Always increasing or just decreasing. When you have a function that is always increasing or always decreasing, it will pass the horizontal line test, which means that its inverse will be a function. And if two functions are inverses of each other, then I can insert one into the other, and the only thing I get back is x. So that indicates that there's an inverse relationship between the two. So just as a review here, if we want to find the inverse of y equals 6x plus 2, we do two things. We swap the x and y, and then we solve for our new y variable. So the fact that we're swapping the x and y, that's essentially causing the domain and range to also be flipped. X for one, it will be y for the other. So now I want to solve for my new y variable. So x minus 2 equals 6y. Divide both sides by 6. And now this is my inverse function. My f inverse is x minus 2 over 6. So these two functions will have flip-flop order pairs. So if there's an xy that lives here, then it's going to show up as y comma x on this one. Okay, we won't worry about example 5. I want us to draw a diagram here that's going to represent the relationship that we're going to see in terms of a function and its inverse. But we're also going to discover there's also a numerical relationship between their slopes at certain points. So let's say we had a graph that looked like this. Let's say we had a function here. We'll call this f of x. And then let's say we have an inverse function that is here. I meant for it to draw it in a way where the two graphs can be overlapped if we were to fold along the line y equals x. And this I can call f inverse of x. So these are inverses of each other. So if there's an order pair on one that is 1, 4, order pair 1, 4, what order pair has to live on this inverse function? 4, 1. Yeah. So that's the order pair relationship here. So Okay. We can obviously tell these are not the same order pairs, but I call them corresponding points because they have that relationship in terms of the x and y's are just flip-flop. Okay. So every order pair that lives on one, I can flip the order pairs and it's going to live on the other function. Okay. So at these points, there's a certain relationship in terms of their slope. I want to see if you can guess what it is. Let's say there's a slope here at this point, meaning f prime of 1 is equal to 7. Okay, so f prime of 1 is equal to 7. What do you think the derivative of f inverse at 4 is going to be? What do you think the slope will be? It's related to this number. 1/7, yeah. Okay, so really, that's it. We're just exploring that relationship. Once we can find their corresponding points, the steepness will just be the reciprocals of each other. Okay, not opposite reciprocal. That's perpendicular lines. It's just reciprocal. So if this is 8, this will be 1/8. If this is 2/3, this will be 3/2. So I want us to look at these points, though. You see how these are not the same x values, obviously, because these are sitting across different locations, but their order pairs will always be flip-flopped. Okay. So I want to create a chart that is going to show that relationship between everything that we've gathered. Okay. So at there's I'm making a table here with 4 spaces, and then the top row I'm going to build that relationship in terms of their order pairs, and then the bottom rows I'll build that relationship in terms of their slope. So here's the relationship. All right. Let's say I have f inverse has an order pair of b comma a. That means f function will have an order pair of a comma b. And if I can find f prime of a, if I can find the slope of the f graph at a, let's say it's equal to n, then I can turn around and say that the derivative of f inverse at b must be equal to the reciprocal of n, which I can say is 1/n. So basically, I'm always going to be starting at this bottom corner here. I'm going to be working my way around this chart. And as soon as I can make my way all the way to this space, then I'm going to have enough data to come back around and say what my slope is. Okay. So let me show what an example can look like for us. So example 6, we have the function x cubed plus 4x plus 2. Find the derivative of f inverse at -3. So this tells us that -3 is the x value of the inverse function, which must mean that -3 is the what of the function, the y value. Okay, so I'm going to build a chart here. I'm always going to start at the bottom right corner. Bottom right corner is going to be what I'm looking for and what I'm going to end up finding at the end. So I'm trying to find the slope of the f inverse at -3. I know -3 is the x value of my inverse function. Which must mean that -3 is the y value of my f function. So the problem is always going to do this. They're always going to ask you information about the inverse slope, but the data they're going to give you is always going to be on the function side. So our strategy is we're going to find everything on the function side and then use this information to help us arrive at what we're looking for. So even though we're looking for information on the inverse function, all of our work is going to be done on the function side. Okay? And we're just going to use that reciprocal relationship. Once we can get to this, then we can get to this number. And we're hardly going to be touching the inverse function because everything given to us is going to be on the function side, mainly. Okay. So even before we look at our problem, we know we can fill out this much of the chart. Okay. -3 is the x value of the inverse, but -3 must be the y value of my function. So because of that, we can work backwards and figure out that, well, -3 must go in for the y value, and I'm going to work backwards to figure out what the x value is. So I'm going to say this. -3 is equal to x cubed plus 4x plus 2. All right, I'm going to solve for x, but I'm going to bring everything over to the same side first. Get the 0 to show up. Now, this is not going to be factorable, but we can find the answer by guess and check. So we're going to try a bunch of numbers and see what is going to cause this equation to be true. That sounds like it's a lot of work, but the numbers that will work, the solution that we're going to find will be a number close to 0. So we can test 0. If 0 doesn't work, we'll try 1. If 1 doesn't work, we'll try -1. After a couple of tries, we should be able to get to our answer. So it'll be a nice integer value close to 0. So let's try 0 first. Would 0 work? If I plug 0 in, am I going to get an equation that is true? All right, I'll get 5 equals 0. That doesn't work. What if I plugged in 1? 1 plus 4 is 5. 5 plus 5 is 10. 10 doesn't equal to 0. Okay. What about -1? Yeah, -1 cubed is -1. 4 times -1 is -4. -1 minus 4 is -5. -5 plus 5 is 0. That's a true statement. So we know the x value here is -1. And once we have that indication, then I'm going to fill in portions of my chart. I know there's an order pair -1, -3 that lives on my function, which must mean there's an order pair -3, -1 that lives on the inverse. So now that I have f of -1 equals -3, I can use this to find the slope of the f graph at -1. So it's kind of like what I'm doing here. I'm gathering information here. Now I'm just trying to figure out what the slope of my f graph is at that point. So I'm going to find f prime of -1. And this number will lead me to this number. Now, to find f prime of -1, I first have to find what? Yeah, before I can find the slope, I need to find the derivative. So derivative should be pretty straightforward. What's f prime of x? Plus 4. So f prime of -1 is equal to, what's the slope of the f graph at -1? What happens if I plug -1 in for f? Equals 7. So if the slope of my f graph has a steepness of 7, then on the inverse side, at a different point, at its corresponding point, the slope here must be what? If this is 7, this must be 1/7. And that's our answer. So we hardly did anything on the inverse side. All of the work that we did is on the function side because that is what's given to us. So that's the strategy for all these problems. We're going to gather our data and then understand there's a flip-flop relationship on the function side, get the derivative, get the slope on the function side, and use that number to flip it, and that's going to be our answer. All right, so example 7. We're going to find the derivative of inverse at 1. Again, I'm going to use my chart. I'm starting at the bottom right corner, and I'm working my way around until I get to my answer. But without even looking at the rest of my problem, I already know that x1 is the x value of my inverse. Sorry, which must mean that 1 is the what of my function. If 1 is the x value of my inverse, then 1 must be the what of my function, the y value. So I know that f of some x value equals 1. So my initial work is always trying to figure out how do I get to my x value because they give me the y value? Okay, so just keep reminding yourself that whatever number they give you is not the x value of the function. Whatever they give you is going to end up being the y value of your function. So we can plug 1 in for the y location and solve for x. This one, we don't have to go through guess and check because I think we can solve this by hand. But if it's a guess and check problem, you should expect a number that is easily found just by going through a couple of checks around 0. Here, I'm going to square both sides. Add 7 to both sides. Take the cube root of 8. What's the cube root of 8? 2. So my order pair is 2, 1 on the function side, which must mean there's an order pair 1, 2 on the inverse side. So if I can find f prime of 2, then this number will lead me to my answer. To find f prime of 2, we first have to find derivative f prime of x. To find f prime of x, what rule do we have to go through here? Chain rule, yeah. Okay. We'll do outsize derivative times insize derivative. I'm going to bleed a little bit into example 9. Example 9 won't take a ton of space, so I'm going to continue my work down here. Do some cleanup here. Numerators together, denominators together. Now that I have my derivative formula, I can plug 2 in to find my slope. 3 times 2 squared, that's going to be 12. 2 cubed minus 7. 8 minus 7 is 1. Square root of 1 is 1. Oh, I forgot about the 2 here. The 2 should be in front. 12 over 2 is 6. So I found my slope to be 6, which must mean on the inverse side, the corresponding point will have a steepness of what? 1/6. Yeah, always just the reciprocal. Don't change the sign. You're just going to flip the numerator and denominator numbers around. 6 over 1 flips to be 1 over 6. Okay. Examples 8 and 9 should be easier because all the data is given to you. We just have to figure out the relationship between all these numbers here. So example 8, we're looking for f prime of 2. This indicates that g and f are inverses of each other. If it says g of f of x or f of g of x equals x, that indicates, okay, g and f have that inverse relationship with each other. They're establishing that for us at the beginning of the problem. Okay, so I'm trying to find f prime of 2. I know 2 is the x value of my f function, which must mean that 2 is the what of my g function? Y value. So even before I look at the rest of the data, I can already fill this in. So sometimes there are some extraneous information to see if students can be thrown off, but what can I fit in here? What's an order pair that has a y value of 2 for my g function? Yeah, g of 7 equals 2. So if there's an order pair of 7, 2 that lives on the g function, there must be a what on the f function? 2, 7. So now I'm at the g function here. If I can find g prime of 7, I can find the slope of the g graph at 7. I can find the slope of the f graph at 2. What's the slope of the g graph at 7? 10. Which must mean that f graph has to experience a slope of what? 1 over 10. That's our answer. Okay, try example 9. See if you can follow the same process there. Okay, what you guys get for your answer? Good. So to begin the process, we know 3 is the y value of my g function. I'm looking for something that fits there. So g of 9 equals 3. So there must be a 3, 9 that lives on the f side. If I can find g prime of 9, this slope will lead me to this slope. So g prime of 9 is -4. I flip that around, I get -1/4. Don't change the sign, you're just flipping your numbers around. Okay, page 7. I want to talk about implicit here, a few minutes. This is page 7. Let's look at 74 here. It says use implicit to find the derivative. Even if it doesn't say to use implicit, we know we got to use implicit because your y variable is not by itself, right? It's stuck inside that natural log expression. There's a understood parentheses here, natural log of xy. So anytime we want to find the derivative and there's a log or natural log involved, we have to always consider, is there an expansion property available to us? I think there is one, right? What can I do with natural log of xy before I explore my derivative rules? Yeah, natural log of product property, right? So natural log of xy can be expanded into what? Natural log of x, what? Plus natural log of y. And the reason that you would want to expand is because otherwise, this is a pretty messy product rule within chain rules. So now we're able to split this problem up into individual portions, and the derivative should be a little bit cleaner. Okay, so now each term we can apply the derivative rule. What's natural log of x's derivative? U prime over u, right? So just what? 1 over x. What's natural log of y's derivative? 1 over y, but we're asking for y's derivative, so we need to include what? ui dx. Yeah, anytime we come across y's derivative, we need to include ui dx. 5x becomes 5. Does the 30 stay? It's also impacted, so 30 is also getting pushed through the derivative process. What happens with 30? Yeah, so just be careful. Sometimes we think that the 30 is by itself. Okay, it's not really going through a derivative process, but it needs to. Right, so now the rest of it is just trying to get ui dx by itself. Dividing by y is the same thing as multiplying by the reciprocal, 1 by y. So you can leave it like this, or you can leave it as this. So this is our slope formula, slope derivative for whatever this graph looks like. I'm going to leave 76 as homework for you, but before I assign the rest of the problems here, there's expansion here, but what do you do with 4xy if you want to find a derivative? What's needed if I want to find a derivative here? Yeah, this is product rule. But this is product property, right? So this you can expand, but this you have to go through product rule. Okay, so your homework is page 7 and 8, 76, and then on page 8, this is all log differentiation. So you do 89, 91, and 93. 89. So 4 problems. 76, 89, 91, and 93. All right, I'll send out a reminder this afternoon. And I'll send you guys a link to the key. You guys can get your phones. Okay, great. Appreciate it. Thank you.